Hey everyone, some things in our world are pretty simple to describe, right? Like a single number can tell you the temperature outside, or how long it took to microwave your lunch. But what about trying to describe the wind? Or say giving someone perfect directions to your house? Well, for that, you're going to need a little more than just one number, so let's just dive right into this.
I mean, seriously, think about it for a sec. If you told your friend to just walk 5 kilometers, where on earth would they end up? They could be anywhere in a giant circle around you. You're missing a really crucial piece of the puzzle, aren't you? You have to tell them not just how far to go, but also which way to go.
And this, right here, this is the perfect illustration of the two kinds of things we're talking about today. Temperature? Easy. Plus 20 degrees Celsius. Done. But the wind, see, the wind needs two parts. It needs a speed, say 15 kilometers per hour, and a direction, like coming from the west. That little difference, that "and" is the key to everything we're about to explore.
Okay, so let's put some real names to these ideas. We're going to break down the difference between what we call scalars, which is basically the what or the how much, and vectors, which add that all-important which way into the mix. So first up, we've got the scalar. Now, this is any quantity that's completely described by its magnitude, which, is just a fancy science word for its size or its amount. It's just the how much part. It's simple, it's straightforward, it's just one piece of information. And then we have the vector. See, a vector isn't complete with just a magnitude. Nope, it absolutely has to have a direction to make any sense at all. It's got two essential pieces, how much and which way. If you don't have both, the picture just isn't complete.
Let's make this super concrete with some real-world examples. So, scalars are things like mass, temperature, or time. These things don't have a direction, right? But vectors? That's things like displacement, which is just your change in position, or velocity, which is your speed in a specific direction. And force is a big one. I mean, you can't just push something. You have to push it in a direction.
So how in the world do we actually, visualize these things? We can't just write down a number and call it a day. We kind of need a picture. And the most perfect symbol for a vector, well, it's an arrow.
And it is so intuitive, it's brilliant. The length of the arrow, that tells you its magnitude. So a longer arrow means a bigger magnitude, like a really strong wind or a much longer walk. And the way the arrow is pointing, well, that tells you the direction, of course. It's just a perfect visual for the whole concept.
Let's use this idea for something called displacement. Okay, imagine you're wandering through a park, right? The actual path you take might be all over the place, long and curvy, but your displacement vector, it only cares about two things: where you started and where you ended up. It's that straight line, that arrow that connects your start point to your end point. The winding journey you took to get there, totally irrelevant to the vector.
Okay, so what happens when you've got more than one vector to deal with? Let's say you walk 3 kilometers north and then you walk 4 kilometers east. How do you figure out where you ended up relative to where you started? Well, you combine them. And the most intuitive way to do this is something called the head-to-tail method.
And really, it's as simple as following the directions. You draw your first vector, we'll call it A. Then, right at the tip, the arrowhead of A, you start drawing your second vector, B. The final result, which we call the resultant, is just a new arrow that you draw from the very beginning of your trip, the tail of A, all the way to the absolute end, the head of B.
Now listen up, because this is a really crucial point. It's a trap a lot of people fall into. When you add two vectors together, you can't just add their lengths. It doesn't work that way. If you walk 1 kilometer north and then 2 kilometers east, you are not 3 kilometers from where you started. The direction changes everything.
Just look at this example of a cross-country skier. Let's say she skis 1 kilometer north, then turns and skis 2 kilometers east. You can see her path basically forms a right-angled triangle. And using a little bit of high school math, the Pythagorean theorem, her final distance from the start isn't 1 plus 2. It's not 3 kilometers, it's the hypotenuse, which works out to 2.24 kilometers. See, the magnitudes do not simply add up.
So drawing arrows is awesome for getting the concept down, but for real, pinpoint precision, we need something a little more powerful. And this is where the component method comes in. You can think of it as the pro move for getting vectomath exactly right every time.
The idea here is it's absolutely brilliant. You take any vector, no matter what weird direction it's pointing in, and you break it down into two much simpler pieces that are perfectly lined up, like east-west and north-south. You can almost think of them as the vector's shadows, if you were to shine a light from above and from the side.
So why on earth would we do this? Because it makes the math ridiculously easy. Instead of messing around with triangles and angles for every single step of your journey, you just add up all the east-west pieces, and then you add up all the north-south pieces. It turns a really tricky geometry problem into simple arithmetic. You just add the columns.
Check out this example from some kind of reality TV challenge. You've got 3 different, complicated movements. But look what happens once we break each one down into its east-west, that's the x component, and north-south, the y component. We just add up the numbers in each column. So plus 38.37 minus 46.36 plus 0 gives us negative 7.99. I mean, it's that simple.
And once we have those final totals, and negative 7.99 meters in the x direction and a positive 9.92 meters in the y direction, we can use that Pythagorean theorem just one last time to find the actual straight line distance. The treasure, it's 12.7 meters away. And that's our how much.
But wait, we're not done yet, right? We still need the which way, and the components tell us that too. Since the x component is negative, which is west, and the y component is positive, which is north, we know for a fact our final direction has to be somewhere in the northwest quadrant. This is huge, because it helps us find the precise angle, 129 degrees, and avoid those common calculator errors.
So we've gone through what vectors are and how to actually work with them. But why should you care? I mean, why does any of this matter? Because this isn't just some abstract math concept. It's a fundamental tool we use to describe the world all around us.
Just think about it for a second. That phone in your pocket, it's using vectors for GPS to figure out your exact route. Weather forecasters, they model the flow of wind and ocean currents with vectors. Engineers make sure bridges are safe by calculating all of the forces, which are all vectors, acting on them. From flying a plane to understanding gravity, vectors are literally everywhere, working silently in the background of our entire world. And that, right there, shows you the power of a really good idea. We started this whole thing with a super simple, relatable problem. How do you give good directions? And just by following that thread, we've uncovered a fundamental language that science and engineering use to describe our reality with incredible precision. So, I'll just leave you with this question to chew on. Now that you know what you're looking for, what other things in your day-to-day life aren't just a single number? What else needs both a how much and a which way to be truly understood? Trust me, once you start looking, you're going to start seeing vectors absolutely everywhere. Thanks for tuning in.